this video we are looking at solving radical equations, and I do have a video already posted of solving radical equations. This is kind of just taking it to another level with the square root function. So what we're going to look at first is we'll look at number 1. And remember, a radical equation is an equation that has a radical expression in it. Radical expression meaning some type of root, cube root, square root, fifth root, fourth root, some kind of fractional exponent for one of your terms. So we're going to be looking at just square roots, but we're going to look at how to solve using these square roots. So the first example we have is the square root of 3x minus 2 plus 2 equals 0. And you got to remember, when you're solving radical equations, you need to treat the radical expression almost like you do a variable when you're doing a regular or solving a regular equation, because that radical expression itself is not going to change until you've taken care of all the other algebraic operations within the equation itself. So what I always do is I take the radical function, or the radical expression, and I circle it. So I know that that is itself a single quantity that I will deal with after I do the other manipulations I need, the addition and subtraction to both sides, division, etc. So the first thing I'm going to look at is I have this plus 2. Well, I want to get the radical expression all by itself. So what I'm going to do is I'm going to take this plus 2 and I'm going to subtract it. So what that's going to leave me with is my radical expression, which is the square root of 3x minus 2. And on the other side I have negative 2. Once again, I'm going to circle and see if there's anything else that I can do before I actually address that radical function. And in this case, there is not. I don't have a coefficient to the radical. I don't have any other constants that are added or subtracted. So I'm ready to actually go ahead and get rid of the radical and try to create an equation without a radical expression so that I can solve it more easily. So since I have square root, we always perform the inverse operation to get rid of a square root. So the inverse operation of a square root would be to square. The inverse operation of a cube root would be to cube. So since I have a square root, what I'm going to do is I'm going to actually square both sides. Once I square both sides, this inverse operation here, I have an inverse on an inverse. That's just going to leave me with my radicand, which is 3x minus 2. Squaring a square root cancels out the radical. It gets rid of the radical for you, kind of alleviates it. So here I have negative 2 squared. So that's negative 2 times negative 2, which is positive 4. So now I have a more manageable equation to solve. And so in order to solve it, what I'm going to do is I'm just going to solve it like a regular algebraic expression or algebraic equation. So I'm going to take the minus 2, I'm going to isolate the variable, so I'm going to add 2 to both sides, and that gives me 3x equals 6. So now I'm left with the final step, which is to get a 1 as the coefficient for your variable. So you divide both sides by 3, so x equals 2. Again, if you want to check your answer, you can actually take the 2 back in, plug it in into the equation for x. So I'll plug the 2 in for x, and see if I come up with an equation that gives me 2 equal values. Well, 3 times 2 is 6, so that would give me 6 minus 2 underneath the radical, which is 4. So I would have the square root of 4 plus 2 equals 0. Well, the square root of 4, as you know, from working with quadratic, can be plus or minus 2. Because positive 2 times positive 2 gives us 4, but so does negative 2 times negative 2. And if you look at the two cases, if I take the positive, 2 plus 2 does not equal 0. So that doesn't work. However, negative 2 plus 2 does equal 0. That does work. Therefore, you know it's a valid solution. So that's how we solve that particular radical equation. So let's move on to the next one. We're going to have multiple steps in this one. So we'll come over here to number 2. And again, I'm going to circle my radical expression. Again, this is a personal preference for me. It helps me manipulate the equation more easily and make sure that I'm doing the correct operations before I actually address the radical and try to eliminate the radical expression from the equation itself. So the first thing I'm going to do is I'm going to look for any additions or subtractions I need to make, and since this is -1, I'm going to add it to both sides. So that leaves me with 2 times the square root of 3z plus 2 on one side and 6 on the other. So that's my first step. My second step now is, once again, I'm going to isolate my radical expression and see if there's anything else that I can do before I do my inverse operation to get rid of that radical. And there is. So I have divided, I've got a 2 in front, and remember, that value is multiplied. That coefficient is multiplied. So the inverse operation of multiplication is to divide. So I'm going to divide both sides by 2. That's going to leave me with the square root of 3z plus 2 equals 3. So now I'm in a situation where, as you saw in the previous example, I only have the radical expression. I don't have any coefficients. I don't have any constants added or subtracted. It's just the radical expression. I do want to make a note here. The reason I did not subtract 2 from either side is because the 2 is actually under the radical. Anything that's under the radical is part of that radical expression, and you cannot touch those values until you perform the inverse operation, which is to square it in this case because it's a square root. So you can't subtract 2 from both sides. You can't divide both sides by 3. These are untouchable until you get rid of the radical. So now I'm ready. I want to get rid of that radical. So I'm going to square both sides. And when I do that, again, we have inverse operation. We have squared and square root. So that leaves me with 3z plus 2 equals, and 3 squared is 9. Run out of room, so we're going to come up over here. So 3z plus 2 equals 9. And once again, we have whittled this down to a simple algebraic computation. We've gotten rid of the radical, so now we're ready just to solve it like a regular old algebraic equation. It's linear. So I'm going to subtract the 2 from both sides. So 3z equals 7. And then my last step is to get a 1 as a coefficient in front of that z, so I'm going to divide both sides by 3. So that's going to leave me with z equals 7/3. And I'm done. And again, if you want to go in and plug in and check, you can go in and plug in and check. So if I want to take that 7/3 and plug it in for z and see if I got the right answer, let's rewrite our equation. 2 times the square root of 3 times 7/3 plus 2 minus 1 equals 5. When I have this situation here, I have 3 over 1 times 7/3. Those are going to cancel out, so that's going to give me 2 equals, I'm going to leave me with 7 plus 2 minus 1 equals 5. 7 plus 2 is 9, so that's 2 times the square root of 9 minus 1 equals 5. The square root of 9 can be positive or negative 3. So we'll try the positive. So I have 2 times 3 minus 1 equals 5, which gives me 6 minus 1 equals 5, which is a true statement. Now let's say I would have had a negative value over here. You could have tried negative 3, because remember, every square root has a positive and negative case. Okay, so let's look at number 3. Number 3 is going to entail several skills that we've worked on, not only the manipulation of the radical equation, but also using factoring to solve for your roots or zeros, going back to quadratics. So what we're going to do is we're going to identify our radical expressions, and in this case, I have 2. So the question is, what do I do with these? Well, this is a special case. I'm going to look at the radical that has the variables, and I'm going to try to isolate that one. So I'm going to take this entire expression the minus 3 times the square root of 5, I'm going to take that entire expression and I'm going to move it to the other side. So that's going to leave me on this side with the square root of y squared plus 12y equals 3 times the square root of 5. And again, I'm looking at my radical expression with the variables. So I've gotten to a point now where I don't have any other options. It would be pointless for me to divide by 3 here, even though I do have a 3 in front of the radical, because I still have another radical over here. We're at the point now where there's a situation where I can actually just alleviate both radicals. Squaring is the inverse of square root, so by squaring I can actually eliminate the radicals on both sides. So I'm going to square both sides. The square root and the square are inverses, which is going to leave me with y squared plus 12y on this side. But how do we do this side? Well, if you were to write that out, 3 times the square root of 5 times 3 times the square root of 5, you would actually get 3 times 3, which is 9, times square root of 5 times square root of 5, which is the square root of 25. Because remember, you can multiply radicals together. The square root of 25 actually is 5, so you have 9 times 5, and that would give you 45. So 45 is my constant term on this side. Now going back to what we did with quadratics, you know that each quadratic has roots or zeros, and we can solve for these roots and zeros by factoring. So what I'm going to do is I'm going to move the 45 over so that I have all the terms together, and that's going to give me y squared plus 12y minus 45 equals 0, which is the way I would set up a true quadratic equation. So now let's get to factoring. I want to solve this by factoring. Well, when you have a trinomial like this, you can use MF-DARM, but we don't need to use all of the steps of MF-DARM because the a value is 1 in front of the y. So basically what I know is in my two factors, I know that I've got to get two factors of negative 45 that give me positive 12. So I'm going to come over here and I'm going to create factoring with 45. So I've got 15 and 3, I've got 9 and 5, and I've got 1 and 45. Those are the ways I can factor this. Remember, since my c value is negative, I'm looking for the difference. I'm looking for two factors that will give me a difference of my b term, which is 12. And when I do all the subtractions here, probably should put that one up top, I get 12 here. So I know my two factors are going to be 15 and 3. So the question is, where do the signs go? I want a positive 12. In order for the 12 to be positive, the bigger factor, the 15, has to be your plus. So now I'm at this point. I've got my factors. That means that either this factor or this factor could equal 0. So let's try both of them. In order to make y plus 15 equal to 0, I subtract 15. Y has to equal negative 15. There's one answer. So if y is negative 15, that will make this factor a 0, which will make the whole product 0. The next one is y minus 3 equals 0. And in order for that one to give you a value of 0, y must equal 3. So those are your two solutions to this particular equation. Now, what you have to be careful of is sometimes you have what they call extraneous solutions. Solutions that when you solve it, you get a value, but those solutions may not necessarily work when you plug those back in. In this particular case, if we plugged in the negative 15, we would get 225, and then we'd get 180, negative 180. So you would not get a negative number underneath the radical, so both solutions are good. And so that's how we solve the radical equations using those. Now we're going to do one more example, solving a radical equation, and that's when we have a radical that has a fraction in it. And so what we're going to do here first is I'm already in a situation where I can't really add or subtract to either side. There's no coefficient. And so I have my, apologize, my different color. I have my radical term. So I'm ready to go ahead and I'm going to square both sides. There's no other step I can take. So I'm going to square this side and I'm going to square this side. Remember, squaring and square root are inverse operations, so that just ends up with x minus 3 over x plus 2. And if I square 2/3, remember that's the same thing as 2/3 times 2/3. And when you multiply fractions, you go straight across. 2 times 2 is 4. 3 times 3 is 9. Okay? So now I've gotten rid of the radicals, so let's go ahead and solve this. Whenever you have what we call a proportion, that's two equal ratios, two equal fractions, we call that a proportion, we solve that by cross multiplying. So what I'm going to do is I'm going to actually cross multiply. So I'm going to have 4 times x plus 2 on this side, and I'm going to have 9 times x minus 3 on this side. Then I'm going to distribute. So I've got 4x plus 4 times 2, which is 8. On this side, I have 9x, 9 times x, 9 times negative 3, which is 27. And I'm ready to solve. So I'm going to get all the variables, first of all, on one side. And to keep it positive, I'm going to take the 4x and move it over to meet the 9x. So that'll leave me with 8 on this side. 9x minus 4x is 5x minus 27 on that side. Now I'm going to move the constants over. So let me move this up a little bit. So I'm going to add the 27 to both sides. So that gives me 35 equals 5x. And once again, we've eliminated all the radicals. So let's do our final step. Divide by 5. Therefore, x is going to equal 7. And if you plug the 7 back in, you'll see that gives you 7 minus 3 over 7 plus 2 equals 2 over 3. 7 minus 3 is 4. So I have 4 over 7 plus 2, which is 9, equals 2 over 3. And remember, when you have a fraction like this under a radical, you can split it up. I can make this square root of 4 over square root of 9. And the square root of 4 is in fact 2. The square root of 9 is in fact 3. So it is a good solution. And that is how we solve radical equations with square roots.